Welcome, friends of the Goleta Valley Library. My name is Tim Brandt, and today I'll be telling you a bit about finding, weighing, and imaging giant exoplanets. Exoplanets being planets around other stars. Since this is a talk about planets, I think it's good to start with the data as we've seen it throughout human history, because exoplanets is even more driven by data than many other areas of science and astronomy. We've really never known what we're going to find until we go out and look. The ancients were the first people to discover planets, the things that wandered in the sky. Planets means wanderer in Greek. And they knew of a few planets. I've shown some of them here. I'm not showing Mercury and Mars because they're very low in mass. The vertical axis here is how massive the planet is. And this is how far away it is from the star. So there's Earth. Jupiter is farther away from the star than the Earth is, and so it's over to the right a bit. It's also considerably more massive than Earth is. Here we're measuring the mass of a planet, how big it is, in Jupiter units. So Saturn's a bit less massive than Jupiter. Venus is about the same as Earth. The first real discovery in planets since the ancient times was the discovery of Uranus in 1791, where there was a renewed interest in watching things moving across the sky, and scientists were able to discover a new planet. Neptune, discovered in 1846, was discovered completely differently, and I'll come back to that method later in the talk. Neptune was discovered because Uranus wasn't quite following the path that scientists predicted based on their understanding of gravity. They couldn't explain Uranus's deviations from this path unless either the theory of gravity was wrong or there was something else tugging at Uranus's orbit. They figured that if something else was tugging at Uranus's orbit, they could predict what it was, where it was, and Neptune was imaged where it was expected to be. After 1846, there was a very long lull until now, 1992, when we weren't able to detect planets around any other stars just because it's too hard. Then in the early 1990s, mid 1990s, everything changed. And you'll start to see planets around other stars popping up all over this plot, where they're at all different masses and all different distances from their star. So these other planetary systems don't necessarily look like our own, with rocky planets in closer to the sun, gas giants farther away. It's a mishmash just all over the place, where there are massive planets like Jupiter very close to their stars, closer than Mercury is to our sun, massive planets far away, lower mass planets far away. And these planets that are being shown were discovered in all different ways. The different kinds of points indicate how we discovered them, and I'll talk about some of those later on. And now there are thousands of points on here. There aren't points in some parts of this diagram, like over here, just because those exoplanets are harder to find. It's not because they don't exist. We're pretty sure they do exist. It's just that a low mass planet far from its star is very hard to find with the techniques that we have available to us now. So watching this movie play one more time, we see the progression from ancient times when we knew just a handful of planets, the bright ones that you can see in the night sky, and of course our own Earth, to the Enlightenment and after the Enlightenment, when we discovered new planets for the first time. 1781 was the discovery of Uranus, and then Neptune in 1846, discovered by the gravitational tug of the unseen planet on Uranus. And then finally, much, much more recently, we've discovered thousands of planets by various methods, and this diagram has been filled up with things that often look nothing like our own solar system. This was not predicted before we started to look. The prediction that many people had was that other solar systems would look pretty much like our own and that our solar system was typical. But it appears now that our solar system is just one way it can turn out, one way among many. And it's, in a sense, made us more special, and in another sense, made us less special because planet formation can do so many different things. This talk, I will focus mostly on the planets that will be showing up here in the top of this diagram shortly, the ones that are labeled by purple diamonds. These are planets that were discovered by direct imaging, which is a very special way of finding planets when we actually take a picture of them. It's the way we found all the planets in our own solar system, but it's an extremely difficult approach for planets around other stars. Here's the first one, whether you want to call it a planet or not. You could call it a brown dwarf, a more massive cousin of a planet. And you'll see a handful of these getting filled out. They're all very big, and they're all very far from their stars for reasons that we'll explain a little bit later. And as time goes on, you see this fill up with just thousands and thousands of planets. So we have a few different ways of detecting planets, mostly by the effects they have on their host stars. So here's one called the transit method, where we look for a dip in the star's brightness as a planet passes in front of the star. The transit method has been used in our own solar system with the transit of Mercury and the transit of Venus actually being measured from different places on the Earth to figure out how far away the sun is. It was a big scientific expedition a couple hundred years ago. For other stars, we can look for these periodic dimmings where the planet passes in front of the star, the light gets dimmer, and then when it comes back around the star again, the process repeats itself. And there were a whole bunch of points on the previous plot that were discovered by this technique. The transit technique tells you how big the planet is, how much of the star it blocks. There are other ways of detecting planets too. Another important way is called the radial velocity technique. This won a Nobel Prize a couple years ago. The idea is that the planet and the star both orbit one another. The star is much more massive, so it wobbles a little bit. The planet is much less massive, it wobbles in this large orbit. But they both do wobble. And we can detect the wobble of the star by looking for shifts in the frequency of its light, much the same way that you can tell whether an ambulance is moving towards you or away from you by the pitch. In the same way, subtle changes in the color of the light can tell us whether the star is moving towards us or away from us, and we can look for these cycles where it's moving towards us and then away from us and then towards us and away from us. These signals are small, and our precision has gotten so good that we can now detect a star wobbling at basically the speed at which an average person walks. Getting somewhere close to that was incredibly difficult, and that's why points didn't start showing up on that first figure until the 1990s. These different techniques tell you different things about the planet. The transit technique tells you how big it is. So if you detect two planets by their transits, you might be able to compare their sizes, at least roughly. The radial velocity technique doesn't tell you how big a planet is, it tells you how massive it is, how much stuff there is. You could imagine that a rocky planet and a gas giant planet could have similar masses, but the rocky planet wouldn't be as big, it wouldn't be so puffy. So the transit technique could tell you that they're the same size. The radial velocity technique would tell you that one is more massive than the other. Put them together, and you know a bit more. But unless you actually image these planets, you can't know that I'm actually talking about Venus and Earth, and that the character of these is so very different, where Earth is the planet we know of that supports life, and Venus is many, many hundreds of degrees with an oppressive atmosphere that would cook you as soon as you landed. So imaging is special. It's only really by imaging a planet that we can understand what it's really like. And that's one of the main goals that we have in observational astronomy over the coming years, is to be able to do this. But it's hard. It's hard because stars are bright and planets are faint. Here, I'm plotting brightness against the wavelength or the color of the light. So the sun's up here, it's pretty bright. If I put Jupiter It's way, way, way down here. This is the reflected light, and this is Jupiter shining by itself, but Jupiter is much, much colder than the sun, and so it shines at a different color, infrared, much too red for your eyes to see. And if I look at the difference between the sun's brightness and Jupiter's brightness, it's about a factor of 1 billion. Jupiter is 1 billion times fainter than the sun. That is roughly the ratio between the light put out by a floodlit stadium and a single firefly. And that's hard. That is far beyond our ability to tell with any telescope today, because this star and this planet would be right next to each other. So imagine being very far away from a stadium and trying to pick out a single firefly within all of those floodlights. It's hopeless with current technology. We hope that we'll be able to push towards that, but it's very hard. What people realized about 30 years ago now is that it doesn't necessarily need to be quite that bad, though. Because that's the way it is today if you're looking for a planet in light it reflects from its star. But maybe if you look at a young planet, it's different. For us here on Earth, we've gotten around this factor of 1 billion challenge by the fact that, well, during the daytime, it's hard to see a planet, but we can just wait till nighttime. When it's nighttime, we block all of the light, or pretty much all of the light from the sun, and so all we're left with is a light from the planet. But we can't play that trick with a planet around another star, so we need something else. And that something else for now, unfortunately, is giving up on the goal of actually imaging these planets in reflected light and using the insight that when these planets had just formed, they would have formed very hot. Our own Earth was probably molten when it first formed. And when a planet forms by the collapse of a cloud of gas or by dumping gas onto something, that process tends to be pretty hot. So a young planet, only a few million years old, for example, our own planet is about 4.5 billion, might be 100,000 times fainter than its star. That's still bad, but 100,000 is a lot easier than 1 billion. And those are the kinds of planets that we are trying to image today. So a few years ago, I started a work with a big collaboration where we were trying to do exactly this. It was a collaboration between 3 countries with a lot of telescope time on a big telescope, the Japanese Subaru telescope. This is only possible because of 2 recent advances. So a factor of 100,000 is still very daunting. We can do it now because we have better detectors for infrared light, which is the light that these planets shine in. They're hot, but they're not hot enough to glow in the visible light like a star is. And also, equally important, have been advances in adaptive optics that correct for the twinkling of the stars. And if you turn it on, then an image that looks blurry like the one I'm showing here snaps into a much sharper focus. All those little points are stars. And if you want to see something faint next to something bright, this image is much, much more useful than, for example, this one. You can see all those faint little points next to the bright points much, much more clearly in this image than in this one. And they are directly comparable. I want to call your attention to the fact that this is not a single dot. It's not a single point of light. It's actually something that we call a diffraction pattern, where if you shine light through a tiny hole, or if you have light from a distant star that comes and hits your telescope mirror, it actually makes this beautiful pattern that depends on the shape of your telescope mirror or the shape of that hole. And this is an experiment you can do in your own home if you have a laser pointer. All you need to do is take your laser pointer and shine it through an index card or something like that, where you poke the tiniest hole you possibly can with a pin. With that tiny pinhole and a laser, you'll be able to create these beautiful patterns, these beautiful interference patterns. And those are the same sorts of things we see on a telescope. So many of the images that I'll show you will look something like this. It's from the same physics, and it's something that you can do in your own home. So that's an image that somebody made that I found on the internet with a laser pointer. I've made similar ones, though I haven't taken such nice pictures of them. Here's an image from an actual telescope. It has many of the same features. You see all these little speckles. They're from interference of light, just like the previous images. Don't worry too much about this in the center. That's just because of how the detector behaves when it has a whole lot of photons. And then our challenge is that we want to find something faint next to this star. So this looks like a speckle. This looks like a speckle. It's hard to tell what's a speckle and what's not. In order to tell the difference, we're going to use a little trick. And that trick is that this interference pattern comes from the telescope. It's not from the star itself. So if my telescope rotates, if only because it's on a rotating Earth, and as the night goes on, my telescope needs to rotate to keep tracking the star, then this pattern will appear to shift. So as my telescope rotates, and this is just because it's on a rotating Earth and trying to keep its focus on the star, the diffraction pattern rotates relative to the sky. Now it's clear. This is a companion. This is something real, and the others are speckles. The other little dots in there are just interference of the starlight. So if I shift to a different frame where I'm keeping my telescope fixed, it looks like this. This isn't orbital motion. This is just from me keeping my focus on the star as the Earth rotates. I can keep going and try to do this for a fainter companion. This is real data for a faint star next to a bright star. If I do this, now making up some fake data for a fainter planet, you can maybe see it down here. And I've subtracted off the average starlight, so you're seeing how it dances around. And all of that dancing around is because my adaptive optics, my correction for that little twinkling that the atmosphere causes, it's not perfect. And so the star is still dancing around, doing its thing, but you can see this planet moving around. This would be very hard to see without the advantage of looking at, of being on a rotating Earth and tracking this as it moves across the sky. If I make the planet fainter still, you can maybe see it, but this is going to run out of steam. And at this point, I can't see it. You can try to do something a little bit fancier. And if you do something a little bit fancier, then you can probably detect such a thing, in this case, about 100,000 times fainter than the star, which is roughly the level that we were at before, where if we had that very young planet like Jupiter, and it were just a few million years old, maybe this is the kind of contrast we might need to be able to detect it. But if that planet were older and fainter, then we'd run out of steam. So that was the idea. We looked at a whole bunch of stars, and we got a lot of beautiful results. I won't talk at all about these, which are disks of gas and dust around young stars, where planets form. What we were really going after were these companions. Unfortunately, we only found 2 of them looking at a few hundred stars. Mostly, we just found blank sky and had limits on what sorts of planets we could have seen if they were there, but they weren't. So in that sense, it was a disappointment. I had hoped to be studying planets, and mostly I ended up studying limits on the population of planets that were the best we could do. The planets are definitely out there. They're very hard to image because they're a lot fainter, but using these other techniques, we found thousands of them. So we need to go a bit further. We haven't found very many planets, but we know that if we keep pushing, we're going to be able to see them and we're going to be able to image them. So we have a few different ways that we want to push towards those goals. To actually find these planets, we're going to improve everything we possibly can. First, the adaptive optics, our fix for atmospheric turbulence. In an earlier movie, you may have seen that diffraction pattern, that image of the star dancing around. We want to limit that dancing around as much as possible, and we want to use clever techniques to get rid of as much starlight as we possibly can. So, with better adaptive optics, we can actually get rid of more starlight and dig down deeper next to the bright star. Another thing that I'll talk about in a little more detail is that those earlier images were from simple cameras taken in a single color. You would let all the light through and you would just take a picture. When you use a phone or a camera and you take a picture, that picture is in color. Every part of the image has a color, and you measure usually three colors: red, green, blue. We're going to do something analogous to what that camera does. Your camera would have little red sensitive and green sensitive and blue sensitive pixels in it. We're going to do something conceptually similar, but a little bit different, to be able to measure the color, or more accurately, the spectrum, everywhere in our picture. And that's going to help us also. And then finally, we can do better with bigger and better telescopes and by going into space. Those are a long way off, and I'm not going to talk about those. Best case scenario, we'll be able to start doing those in about 10 years, a little bit less if you're being very optimistic. The University of California is a major partner in the 30-meter telescope, which is a proposed planned telescope that would go on either Hawaii or the Canary Islands. Its status is very much under debate at this point. It's been somewhat controversial, but it would give us the power to be able to image some of these planets around other stars. My specific project that I'll talk about is called CARIS, the Coronagraphic High Angular Resolution Imaging Spectrograph, which is less tortured than many of these acronyms are. And it's not a simple camera, so I'll walk you through how it works and what it actually does. It's called an integral field spectrograph, and so just like a camera on your phone or a regular old digital camera, it's going to take a color picture. Everywhere on your picture, you're going to have color, or in this case, even a spectrum. So we're then going to be able to reconstruct a full color image at the end of this. The way it does that is not the way your phone does it, where you have red pixels and green pixels and blue pixels. Instead, what we're going to do is we're going to use these things called lenslets, where you have an image right here, and then each little part of that image is going to be focused by the lenslet into a tiny little point. And so you're going to have a whole bunch of dots after that lenslet array. Imagine an image, but very, very pixelated. And then, since these dots have a lot of space between them, we're going to spread out those dots using a prism. So rather than red, green, and blue pixels, we're going to use a prism, and we're going to make a rainbow for each little lenslet, a rainbow for each little part of the image. So to go over how that actually works in a sequence, this is a diffraction pattern, kind of like what you've seen before. And it has different intensities all around the image. This is what you would see at the lenslets. If we just put a detector at the lenslets, then you would see an image kind of like we saw before of this diffraction pattern. When we use the lenslets, all the light from this area, for example, gets focused down to a point. And so after the lenslets, you have a whole bunch of little dots. Each of the dots is bright, and there's dark empty space between them. We then use that dark empty space to spread out each point. So each point here becomes a rainbow. In the same way that if you have a beam of sunlight, you split it with a prism, it becomes a little rainbow. And so here are our rainbows. I haven't colored them by the color as you would perceive it. This is all infrared light, which is too red for your eyes to see. But think of this as a rainbow for each lenslet. Each lenslet has a rainbow. And these little dark areas are regions where the sky actually doesn't let light through. The sky blocks light. So a rainbow with a little bit of region here and here where water and carbon dioxide in the air block some of the light. We can then use the rainbow to reconstruct what the image looked like. So this image is stepping through color from the bluest color first, here, to the reddest color last, here. You can see that at different colors, the image looks different. This pattern is bigger. You can do this experiment yourself again with a laser if you happen to have a red laser and a green laser. The red laser is, well, redder than the green laser. The red laser will make a larger diffraction pattern on your wall than the green laser will. The same thing happens here. The bluer light has a smaller diffraction pattern than the redder light. And so you can see this whole diffraction image just expand. But there's one little thing that isn't growing with the image. If you look closely at this point over here, which I'll circle now for convenience, if I can do it, there it is. So now I've circled this little point. It is not moving outward with wavelength. That's because it is not part of the star's diffraction pattern. That's actually a brown dwarf. So this is a more massive cousin to a planet, and it has its own diffraction pattern, but it's not part of the starlight. And so you can see it's separated from the star right here in one image. This is one image. In the images that I showed you before, in the movies that I showed you before, we had to wait for the sky to rotate. It took maybe half an hour to be able to really tell whether something was a companion, a planet brown dwarf, or whether it was just a speckle, a part of the diffraction pattern. Now, because we measure a rainbow for each lenslet, we can tell immediately. And that's part of the power of these new instruments that tell you the color, or more accurately, the spectrum that hit each individual lenslet. Keras is part of a new generation of instruments. We're not the only ones doing these sorts of things. I've put two other ones on this slide, and those are both at the Gemini telescope and the VLT telescope. These are big telescopes in Chile. Gemini has a relatively small instrument called GPI, about the same size as a person. Sphere is a gigantic instrument. The Europeans are very good at building big instruments. A person would stand on this platform. So Sphere is a much, much more ambitious project, but it works fantastically well. There is one major advantage that we have as Keras over GPI, and I'll show that in just a minute. Here's Keras before it actually got shipped. You can see the Iron Man red cladding we had. And inside, this is what the optics look like. The power that Keras has relative to some of these other instruments is that we can cover a huge range of wavelength. The range of wavelength, or the range of color of the light, lets us tell whether something is part of the diffraction pattern or whether it's a real companion. If you look closely over here, this is a fake companion, a fake planet that I put in the data set. And you can see the speckles washing over it in this image that covers a huge range of colors. Here it's a little harder to see because you don't have quite the same range of colors to be able to follow the speckles as they wash over the planet's location. In practice, this really does help. So here are some famous directly imaged exoplanets. There aren't that many of them, so this is a very famous system. And this is without using this color to distinguish planets from speckles. So here we've removed the starlight as best we can. That's what's in the center is we've just masked out where it's removing the starlight is completely hopeless. And these little spikes are from our imperfect subtraction of the starlight. This is a planet, and a planet. And if we use our knowledge of how diffraction scales, and we use our wavelength coverage, then this inner planet pops out much, much more clearly. So it lets us see these planets in a way that we wouldn't be able to otherwise. We can do more with spectra. Spectra tell you in physics and in chemistry what something is made of. Different elements glow in different colors. Different molecules glow and absorb different colors. So this is a spectrum of a planet or a brown dwarf, depending on what you want to call it. The brown dwarf is just the more massive cousin. And you can see all these jagged lines, all these wiggles in the spectrum. Those wiggles and those jagged lines are fingerprints of carbon monoxide, of water, of methane. So by measuring the spectrum and measuring those wiggles, here's a model. This model doesn't have any noise associated with it. The wiggles in this model are purely from chemistry. So we can measure the chemistry of an exoplanet if we can measure its spectrum. And that's what we get with direct imaging. CARAS doesn't have quite the ability to measure all of these wiggles that I'm showing here, but it still can measure these shapes, and these shapes still do carry the fingerprints of molecules like carbon monoxide, like methane. They still do carry the chemistry of these exoplanets, and that's something we can only get with a spectrograph. This is something that's been done for a little while now, including with the Subaru telescope, the telescope that I've mainly worked on. So here is an example. I'm showing you the spectral fingerprint of methane. Methane is a greenhouse gas. It's also a natural gas. You burn it if you have gas heating or a gas stove. And it absorbs at many wavelengths in the infrared. That's what makes it a greenhouse gas. So here I'm showing how much light gets through and how much light gets blocked by 1 microbar of methane. That's the current concentration of methane in the atmosphere. Before the Industrial Revolution, it was a little bit less. If I crank up the amount of methane, then I'm going to absorb more and more and more light. And so, as I crank it up, all of the light in this part of the spectrum gets blocked. So this is now a very large amount of methane, far, far more than we have on the Earth. But on some exoplanets, methane is chemically favored. There is a lot of it. On the Earth, methane combines with oxygen in the atmosphere and gets destroyed. It can be combined with ultraviolet light from the sun. And in a few years, the methane molecule will be destroyed. But in planets with different chemistry that don't have oxygen like the Earth does, methane can not only stick around, but can be produced in abundance and can be the way that carbon and hydrogen join together. If we look at some model planet spectra, then as you cool down from a hotter 1200 degree Kelvin planet to a cooler 600 degree Kelvin planet, that would be about 300 degrees Celsius. So still pretty toasty by our standards, but cool compared to many of the things that we're actually imaging. In this cooler planet, all the light is gone here. There is very, very little that we get at these wavelengths, and that's because there's so much methane in the atmosphere. So if we see a planet and there's lots of light at these colors and not much light at these colors, that's a fingerprint of methane in the atmosphere. And indeed, we see such things. Here, this is a picture taken at the colors where methane lets light through. This is a picture taken at the colors that where methane doesn't let light through. You see the planet there? You don't see it there. So this planet has a methane-rich atmosphere. With this image, we can tell what the chemistry is in this planet's atmosphere. So all this is incredibly powerful. The downside is that looking for planets around bright stars has been very challenging, and we haven't found very many of them. So, unfortunately, the history of the field has consisted of promises of finding a lot of planets and doing great science, followed by finding a few planets and, well, still doing great science. But if you want to be a bit of an accountant, for example, and figure out how much it actually costs to find a planet, then the numbers don't work out quite as well for imaging as they do for something else. I've roughly guessed here that we have spent something like $200 million trying to image exoplanets. And since we've imaged about 20 of them, that comes out to about $10 million per planet. These planets are special because we can measure their chemistry. We can measure things about them that we can't for other planets. But still, if you just naively compare that to something like the Kepler satellite, which found a couple thousand planets, then the price is very different. So our imaging planets are special. They're worth more, but they cost a lot more. And part of that is because we've just been looking around stars and hoping we get lucky, hoping that we see something that we can image. And we need to do better. And now we do have an opportunity to actually do better. And that's going to be the last part of my talk. That approach that we can do better now is thanks to astrometry, where we measure not the wobble of a star as it moves towards us or away from us, but as it moves in a tiny little arc across the sky. It is indeed a tiny arc. For a nearby star with a planet orbiting around it, this arc that we're looking for is basically equivalent to trying to see something going around in circles the size of a human hair if you're looking at that human hair from here to Los Angeles. So it's like looking at the width of a human hair 100 miles away. It's very hard. These, these motions are just unbelievably tiny. But thanks to this new satellite the Europeans have launched called Gaia, we can actually pull it off. So, astonishing as it may be, we can actually measure the motions of stars with that kind of precision, the width of a human hair, as seen in Los Angeles from Santa Barbara. And that's going to let us trace out the orbits of stars as they are tugged by their unseen planets across the sky. It's complementary to these other techniques, and it's incredibly powerful. So Gaia right now is measuring billions of positions and proper motions. There were no accelerations, though. These wobbles that this satellite was measuring weren't until, well, it says 2021, but it's actually been pushed back a little bit now to 2022 at the earliest. So what we're going to do to get around this fact and be able to figure out which stars are being tugged by planets now, we're going to use something that the Europeans launched a while ago, Hipparcos, that measured positions, that did the same sort of thing, just very, very precisely measuring where the stars are 30 years ago. It's going to work in the following way. 30 years ago, Hipparcos would have measured a star here, and it would have measured it going in this direction. Gaia now measures a star up here going in this direction. So the direction the star was going when Hipparcos flew is different from the direction the star was going when Gaia flew. But even more than that, we have the position in Hipparcos and the position in Gaia. So that gives us the average motion of the star. So we have three motions that we can compare: the motion that Hipparcos measured, the motion that Gaia measured, and the difference between the positions that Hipparcos and Gaia measured. We can compare these to look for stars that are being tugged across the sky by something that we can't see. Gaia and Hipparcos observed a lot of stars, and so since we have this information for right now 100,000 stars and soon millions of stars, we can choose which stars to observe. We can choose to look at the stars with our big telescopes that are being tugged, that likely do host planets and brown dwarfs. So we can stack that deck. Before, our odds of finding something were something like 1%, if even that, which is pretty depressing. But by stacking the deck, we can potentially do much, much better and bring down the cost and bring up the science of these directly imaged exoplanets. Here's an example. With the first brown dwarf that was imaged, it was actually the first diamond that showed up in the very first movie. It was discovered by imaging, and now, thanks to this motion across the sky that we can measure, we can identify that its host star is being tugged across the sky, and we can even measure the mass of this brown dwarf. So it turns out that its 70 Jupiter masses, almost a star. This is something that we would never have been able to figure out without this new technique. It's not just good for weighing planets and brown dwarfs, it's also good for finding new ones. So here, this is a star that we looked at because it was being tugged across the sky. We observed it with our big telescope, and lo and behold, we found a brown dwarf next to it. So something that we wouldn't have found before, but we knew that if we observed this star that's being tugged across the sky, we had a better shot. So we were able to load the dice and actually find this new brown dwarf. And not only that, we were able to weigh it. Weighing these things has historically been something that only radial velocity can do. So now, this is a special technique because not only can we find them, we can also weigh them. And so we're starting to weigh planets now and brown dwarfs in a way that we've never been able to do before. This one is about 46 Jupiters, so also pretty massive. But we're pushing this technique lower and lower in mass, and we're starting now to weigh planets around other stars, both weighing them and finding new ones to image. Here's one that we haven't imaged yet, but it's very reminiscent of the case with Neptune, where we could tell that Neptune was there based on the motion of Uranus that wasn't quite what we had predicted. In this case, the star is being tugged across the sky in a way that we didn't predict. And so that tells us, in combination with our measurements of the wobble from radial velocity, it tells us what's tugging it and where that tug is coming from. So in this case, we know not only how massive this planet or brown dwarf is, we know where it is, we know where to look. So just like with Neptune, where its mass and its location in the sky were both predicted before it was imaged, we can start to do that now with planets around other stars, something that has never before been possible, but is now thanks to these incredible new telescopes that we have. So finally, I think that after many, many years of under-delivering on our promises, we are finally poised to deliver the wonderful science that we've always hoped to be able to do, where we can identify which stars host the planets that we can image. We can then image them, and we can take their spectra, we can measure their temperatures, we can measure their chemistry, we can understand what these worlds are like. So this still needs some time, and it will benefit enormously from more powerful telescopes. But with these more powerful telescopes, we'll be able to image dozens of these worlds and understand what these worlds are really like, what their chemistry is, what their atmospheres are like, what their characters are. And so with that, I will conclude that I think the golden age of direct imaging is finally on the way. And thank you.